Welcome to video 2 of the biomimicry series. In video 1, we explored high-level biomimicry, gave some examples, talked really about the mindset of biomimicry and how we can apply it to Urbana-Giron group, or how we already are applying it. In this video, I want to dive a little bit deeper and start to unpack the application of biomimicry, to how you can bring it to your own practice, or you could create your own practice in biomimicry. And really what I want to emphasize is that if you look at some of the great examples of biomimicry out there, none of them are really following a hard and set methodology. There's no one way of doing biomimicry. Instead, those people are often following a question or a passion. They see something inspiring in nature and want to bring it into their practice. So what I'm going to share is not a defined methodology. Think of it more as a set of tips and tricks that I've picked up along the way that I find can be effective for helping you frame your biomimicry mindset. This video is going to be broken up into 3 parts. In part 1, we're going to talk about some of the basics, some of those tools and methodologies that are out there that you could use. Part 2 is all about the bias, which I think is an underrepresented conversation in biomimicry education. Biomimicry is fundamentally a mindset. So in order to adopt this mindset, you have to recognize some of the biases, the beliefs, and the things that you hold that might be holding you back from really doing biomimicry. And number 3 is about bridging. And what I mean by that is I want to explore, how do we shift from this rooted system that we've created that's degenerative, that's not sustainable, into one that's regenerative? How do we move a rooted system? So let's begin with the basics. As I mentioned, biomimicry is fundamentally just shifting your perception. It's about recognizing that nature does packaging. Nature creates complex materials. It does adhesion. It deals with transportation, movement, circulation. It creates complex structures, communities. It does circularity. It embodies or sequesters carbon. It's doing a lot of the things that we're doing, but doing so a little bit differently. And so when we look outside, what's amazing from this biomimetic lens is that we're looking at the culmination of 3.8 billion years of research and development. So what you see is what's lasted. Nature will remove the things that are unnecessary or that don't work anymore. So we're looking at this textbook of bright ideas that we could bring into our own design solutions. And a simple way to kind of frame this conversation is to look at biomimicry in 3 different categories. The shallow and simplest is emulating nature's form, where we copy shapes in nature. A little bit deeper is when we start to emulate nature's processes, how nature manufactures, how nature behaves. And the deepest and most important is when we start to emulate nature's systems, starting to reintegrate ourselves into nature by understanding her principles, kind of her brushstrokes, the way that she creates, so that we can, more harmonize with that system rather than try to control and dictate that system. As I mentioned in video 1, that systems level biomimicry is important because it's expensive fighting nature. Nature abhors gradients. It will dissipate gradients that we create between the built and natural environments. And the more, we try to resist it, the more energy we're going to put into it, and ultimately the more greater for potential collapse. And we'll talk about that. But those are the 3 ways you can look at it. And form-based biomimicry is one that you see often in architecture, copying shapes in nature. And this is great because it can tell a really interesting narrative. It can tell this beautiful story. But to me, that's not really biomimicry. Fundamentally, biomimicry is copying function. It's like when you want to copy a shape for a reason. And we'll talk about that later on. But I want you to kind of think of, like, when you do form-based biomimicry, are you copying shapes just for an aesthetic story? Because nature's shapes are all there for a reason. Nature manufactures shapes to be efficient at something, whether it's material and resource use, whether it's doing something outside like reflecting or collecting. You got to think about that function that nature is achieving through that form. For example, the bullet train is one of the classic examples where a birder improved the Japan bullet train by copying the beak of a kingfisher, improving its efficiency, its speed, and ultimately reducing the noise that was created as the bullet train went through a tunnel, creating this pressure buildup that when it exited the tunnel created a sonic boom. I talked about that in video 1, and you can find out more details about this and all of the examples that I share in subsequent materials. Another classic example is whale power, which emulated the bumps of a humpback whale fin to improve the efficiency of a wind turbine blade. Applying that tubercle technology to a blade made it 20% more efficient. The blade ran at slower wind speeds, and the blade was quieter than traditional blades. So you can see it's not just about copying shapes for an aesthetic appeal, but actually for a function, for improving efficiency. This is a kind of a cool example where shark skin has been used to inspire more efficient fuselage in air transportation. You may remember Speedo back in the early 2000s emulated shark skin and applied it to a bathing suit. I think it was the Sydney Olympics coming up at that time. All the swimmers used this shark skin suit, and world records were being decimated because of how efficient it was. What's neat about shark skin too is that bacteria can't adhere to it. So they've used this film for antibacterial tapes and adhesives. Lufthansa has actually applied this to a fuselage on their Boeing 777, and this skin is actually reducing fuel consumption and carbon emissions. In architecture, form is often used. This is a cool example of the Eden project where the architects and engineers were tasked with trying to create a structure on a unstable, irregular topography. And they were doing so on this quarry that was being mined, and it was actually still being mined. So there's no certainty on the final shape of the site. And they looked at nature as to how to create structure off of this irregular, perhaps dynamic kind of foundation to make the Eden project. And again, as I mentioned in video 1, we're already doing biomimicry on multiple levels within Urbana-Giron Group. This is one of our great case studies of working together. RBG, Atelier 10, and B+H architects all work together to make this 101-story tower that used biomimicry in its form and in its process. So, emulating the rooting system of mangroves, this tower was being built in a dynamic delta where the sand is dynamic as the water. And so we looked at root systems in the area to see that, the mangrove has this beautiful rooting system that has multiple kind of foundations coming out, creating stabilizations or helping stabilize that sand or that foundation, dissipating the water energy. And we use that as a metaphor. We looked at bones to make more efficient structural members. We looked at dragonfly wings for how to wrap this building. And we also looked at the Fibonacci sequence for how we can do that spiral effectively, saving materials and fitting into its ecosystem. So like I mentioned, form-based biomimicry is copying shape, ideally to improve efficiency, but it doesn't take us away from some of these practices that really separate us from the rest of the natural world. This idea of heat, beat, and treat manufacturing. So process biomimicry is looking to nature for how we can copy the way nature manufactures. To give you an example, think of spider silk. Spider silk has a strength to weight ratio greater than anything we've ever created, but it's manufactured at body temperature, body pressure. It's water-based chemistry. It uses only the energy of the sun, and that spider will actually eat that material. So it's fully regenerative, fully recyclable. That's the next level of biomimicry, is when we can copy processes in nature. Some cool examples is a hospital in Mexico has figured out a way to make a building eat smog. So in the 90s, Mexico was one of the most polluting cities in the world. It was a major challenge. So how do we move from that toxicity to something more regenerative? They created this facade. Elegant Establishments made this facade that has this very organic shape, and the shape had a reason. The shape actually was more conducive to inspiring flow through that facade. And the reason they wanted that is they wanted the smog to touch as much surface area as possible, because this facade actually ate smog. It was amazing that there's this film made of titanium dioxide, a pigment, that when that titanium dioxide mixed with the sun and the smog, it actually decomposed and reduced that smog to less harmful byproducts, and would actually absorb and neutralize that pollution. Al-Bahar Towers is a classic example of biomimicry where they've added, again, the second skin that adapted to the kind of the solar transition, the solar movement. And what they're able to do is these semi-autonomously responding kind of facades were able to reduce the solar gain by 50%, reduce energy consumption by 50%, and therefore slash CO2 by almost 2 tons per year. What I like about this is that, instead of thinking homogeneously, this tower was able to follow the sun the same way that nature follows the sun and uses its processes to maximize its efficiency, instead of just coating the whole building with the same kind of design and homogeneous structure. Another cool example is Blue Planet. Concrete is one of the most carbon intensive processes that we have in the built environment. It emits a lot of carbon, but in nature, carbon's not a problem. In fact, carbon is a building block for life. And this is, most beautifully emphasized in coral reefs. So coral reef is very similar to structural concrete. It's a foundation, it's a base, it's very hard and rigid. But what's amazing is that corals are actually made from just salt water and CO2. Together, they're combined to make calcium carbonate, which is a material similar to Portland cement. Blue Planet has figured out a way to copy that process to make a material that actually sequesters carbon in the manufacturing of concrete. So they're able to mineralize 440,000 tons of CO2 per ton of concrete production. Another cool example when you think about biomimicry at a process level is how does nature avoid collisions? You think of swarms of bees, you think of locusts, you can think of the birds and the way that they create that beautiful architecture in the sky. Well, Volvo went to nature to figure out how do we bring that to our automotive industry and avoid collisions in our cars. They're able to understand locusts and the way that they use signalings that bypasses the brain and goes right to the wings to apply to anti-collision technology in their cars. And again, we're already doing biomimicry. These next examples are how Atelier 10, which I think is a great descriptor of biomimicry at a process level. Atelier 10 is focusing, and a lot of us are focusing on how do we sequester more carbon, create circularity, create passive designs, how do we leverage resources more efficiently and leverage seasons. In their Federation Square, they created this termite-inspired passive cooling system. It was one of the biggest kind of maze cooling systems at the time, and they're able to maintain an atrium space in 40-degree ambient temperature swing, so swinging from, let's say, 42 degrees to 2 degrees Celsius. They're able to maintain a constant temperature through this termite-inspired process. Their Roosevelt Presidential Library used the living building standard as their design standard. And to me, the living building is one of the standards that is closest to biomimicry. It's talking about using local materials. It's talking about leveraging free energy. It's about regenerative design. And this is what Atelier 10 did in the Roosevelt Presidential Library. They used local materials, they used regenerative design, which included bringing in agriculture to create kind of regenerative landscapes. The system is a carbon sink. They used the energy of the sun effectively. They leveraged free energy. And what I loved is they also used shape over material. Nature is very clever at using its shape and using information before it uses materials. So making this kind of building that is kind of embedded into its ecosystem, this shape that is making it more efficient and more effective. Atelier 10 also worked on a biomimetic office building, using complex kind of forms to make sure that it's capturing the sunlight as efficiently as possible. They used genetic algorithms to make sure that the layout of the building was going to be most effective. They used shape in the upper atrium to maximize daylighting. They used adaptive facades like sensitive plants. And they made sure that this system could all be self-heated, self-cooled, self-ventilated, so that it could emit chiller for the building. The other cool thing is that this brought in biophilic design as well, which they proposed was going to add 25% more productivity. There's quantifiable research that shows connection to nature improves concentration and efficiency. So there you go. Form-based biomimicry is copying shapes. Process is copying the way nature manufactures. And the deepest and most important is systems level biomimicry when you copy nature's principles. The way that we do this is that every project starts with a living story. And a living story is trying to understand what the land wants to do, what it will support us in doing, and what it will permit us to do. It's really about understanding that story of the land, the trajectory of that landscape, as if we were never going to be a part of it. Because if we know where the land wants to go, then we can integrate designs more efficiently and effectively so that we're not fighting nature. It's a resiliency strategy by trying to work harmoniously with nature. In our new Lowell's living story, this was exemplified in the way that we've followed the water. And water is the first architect of the landscape. It will shape the design of the place, and it will shape and inform the design of our places, our built environments. In this design, we also wanted to make sure that we went beyond this idea of doing less harm and we're actually regenerative, that we created a system of architecture and infrastructure that contributed to its place. And to do so, we measured the ecological performance of that site before the design and after the design to show that our design is actually improving carbon sequestration, oxygen production, air purification, temperature regulation, and things like that. So the systems level biomimicry is learning those deep principles. Another example is that we worked with Guelph on their $10 million circular food economy. It's the first circular food economy in Canada. And we mapped out the city of villages. We imagine it a bunch of patches, which is an ecological model, looking at each village as a little patch, understanding what are the resources and the opportunities, the pressures in those little villages, so that we can make locally attuned and appropriate kind of decisions for the circular food economy. We built this technology that mapped out where everyone was growing what in their backyards and able to coordinate that. Instead of everyone growing cherry tomatoes, we started to be more strategic and said, maybe Amy could start growing fruit trees and so on and so forth. This helped us make a resilient food system in the village. And it came at the time of COVID when we're seeing kind of the influence and the vulnerability of our food system. So there it is, form, process, and system. Form is the easiest, the sexiest. You can see that translation from biology to design, but it's in the process and the systems that we really want to strive to do things more effectively. The key, though, to doing biomimicry in all of these examples is that we want to know the function that we want to achieve. Knowing the function is the bridge between biology to design. And what you're really trying to understand is, what do you want your design to do? And this goes to the bias part. Often as designers, when we have a design challenge, we go to what we want to design. We just pull on old ideas, which is much more efficient, and that makes sense. But in a time where we need innovation, we need really like bold thinking. Instead of just going to what you want to design, maybe take a moment and think, what do you want your design to do? Because that will help you bridge to the natural world. For example, let's say you're working on a project and you want to manage circulation, you want to manage flow. That's the function. When you think of managing flow or managing circulation, then you could start to think of things like veins, or think of swarms, or you think of ant colonies. You think of adhesion, you might think of geckos, or you might think of worms or snails or snakes. Another example is like, if you want to integrate nature and design, you want to integrate things into a built environment. You look at a bunch of different examples for how nature manufactures structures on members or columns or other materials. And the point is, you just might find inspiration. You don't have to know exactly how to do these things. You don't have to have a biology degree. In fact, that's one key element. Is I dropped out of biology, and I think it's effective that you don't have a deep biology degree. A lot of us have a general understanding, and a lot of us has a perspective that could really leverage biomimicry. We could look at something from our own lens, whether a structural engineer or an artist or a business manager. We're all going to have a bias that's going to look at nature, and we can pull ideas from that bias. So here is kind of a methodology that we can apply. The first stage is to identify what it is you want your design to do. Identify that function. Once you have that function, you can start to look at nature. And I'm going to give you an example. If you all look at this image, what is the function of a stapler? Take a moment just to think about, what does a stapler do? You may think it sticks, it adheres, it collates, it puts things together. Those are those functions that we're looking for, those verbs. It also, has a piercing technology. So it's piercing, it's penetrating, it's kind of striking. Once you identify those functions, then you get to go to the natural world. And there's a great tool out there called asknature.org. It's a kind of like a Wikipedia for nature-based ideas, so that you type in your function, and it's going to show you a bunch of examples in nature that achieves that same function. So if we go to adhesion or piercing, going back to that stapler example, we might find geckos, we might find snails for adhesives. We might think of mosquitoes or birds penetrating the water for how to penetrate or how to pierce. The next level, once we have those examples, to break it down even further, we might want to look at the context that they're doing it in. So the stapler is in a dry context. It's like trying to pierce a certain kind of material. So maybe there's examples that are more appropriate than others. There's a great example of Jeff Karp, who's a medical doctor, who made an adhesive for a heart stent. When there's a laceration on a heart, they would have to use these staples, and these staples were kind of weird and they didn't work that well. So he looked for an adhesive that worked in a dynamic environment because your heart is beating, and in a wet environment because you're working within the body. So he looked at muscles underwater that were able to adhere to things, and made an adhesive that's now, one of the most popular heart adhesives out there, because he copied something in nature that adhered, but he also copied and learn from the context. He went to the context that was most appropriate for the context he's dealing with. So when you identify that function, you look for natural resources, or examples, and then you can study the context. Then you can start to abstract ideas. And there's more details on that in the subsequent materials, but I just want to give you kind of high level. The other thing that's important is that there's two ways of thinking about this. For us, often we're going to take design challenges to the natural world, but there's also another way of thinking about it where you just take biology to design. And what that means is that it's really about those who just study with nature or get obsessed with nature. Think of those questions you had as a 5-year-old, like how does a cat jump so high, or how can an ant carry so much load? It's when you take that problem or that kind of inspiration and just sit with the natural organism or the natural system and start to abstract into a design challenge. This is one of my students who took a barrel cactus and applied that, reverse methodology to say, like, what is happening here? What is nature doing here? Making generalized assumptions and then finding ways of those technologies applying to a built environment. So self-cooling, for example, by copying the barrel cactus, or creating microclimates.